Okay, yeah, so we started recording. Okay, so everyone, I apologize for like the first thing of like this setup and stuff like that. But then now hopefully a few of you at least some of you should have been able to get started and then have a working instance of the notebook. In this case, right? So let's actually begin with this with the talk for today. So the talk for today is going to be on natural language processing. Basically, how do we teach machines language? Okay. So here are the files for the workshop, and then like here's the attendance that you may want to scan later on. And here is the roadmap for today. Okay. So first we'll be covering NLP. What is NLP in the first place, right? Why have we all come here? We'll be covering the basics of NLPs, the key terms behind it, and so on. Then what we'll be going into is data processing. So how do we clean and process text data? Because text is an extremely inconsistent type of data, right? It can occur in all shapes and forms and stuff like that, right? Now, we also have we have the thing of tokenization, basically converting the text into a form that is understandable by a machine, right? Then we'll go into basic models, i.e. a naive Bayes model to solve the problem that we'll be handling for this workshop, okay? Then finally, we'll be looking at attention models, like we'll be looking at the attention mechanism, and then we'll be leveraging a pre-trained BERT model to classify movie reviews, all right? And then finally, we'll be looking at current advances. We'll be looking at the current state of the art for natural language processing, all right? And we'll have a small hands-on with GPT-3, okay? So now I'm sure that everyone has heard of this story that came up recently, right? There was this engineer at Google who had basically claimed that an AI that he was working on had gained sentience. So I'll basically, like, if you haven't gone through like the full excerpt of the conversation, here are some extracts. So here they basically, Lemoyne is the name of the engineer and Lambda is the name of the AI. So the engineer was basically like talking to the AI, trying to determine what the AI was actually thinking. And the AI was actually like able to come up with all of these like sort of very insightful analysis of certain Venn cones and stuff like that. As well as some very, very concerning text over here. So here's the question, right? Was Lambda actually sentient? Is Lambda sentient? The answer is no, it isn't. What it is very good at natural language, right? It can speak almost just like a human. If we're going by the bar of the Turing test, Lambda would probably pass. The question is, how did we train computers to get so good at language, right? That is what we're going to be talking about today. The answer is through natural language processing, okay? So first, we might be asking, what is NLP or natural language processing, right? So natural language processing is, okay, fine. In such a case, let's just ask Google, right? We ask Google for literally everything. So Google basically gives us this definition, saying that NLP is a branch of artificial intelligence that deals with analyzing, understanding, and generating the languages that humans use naturally in order to interface with computers in both written and spoken contexts using natural human languages instead of human computer languages. Okay, this is extremely wordy. Let's break this down. So here's the key thing about language, right? Language is hard. There are so many things that can change the meaning of words. Tone, punctuation, capitalization, surrounding context, idioms, euphemisms. There are so many things where a small change can actually completely change the meaning of a sentence. For example, right? Here's a particularly disastrous example. Let's eat, kids. Just remove one comma over there, and it becomes let's eat, kids. and Jeffrey Dahmer wants to know you. So basically, right, that's the thing about language, right? Language as a whole is not a one-to-one mapping. It's not easy for us at times to pass out the meaning of language, right? So how do we expect a machine to deal with it? Especially considering the computers are extremely stupid. This is not a knock against it. I know that the processing power is great and stuff like that, but that's not what I mean. They can only operate on very well-defined instructions. And language in itself is inherently messy, right? You basically have puns, you have metaphors, you have so many different ways to twist language. You basically, I'm just just read any sort of well-regarded book, you'll just see how language can be twisted and turned, right? So computers don't deal well with uncertainty. You need to give them precise instructions. So what is the key challenge of NLP? Given all of this context, what would you say is the key challenge of NLP? I would say that the key challenge of NLP is converting an inherently messy structure like language into a well-defined structure for a computer. That is the main challenge of NLP. How do we convert the inherently messy and abstract concepts of language into something grounded and well-defined that a computer can understand, because they're only capable of understanding zeros and ones at the end of the day, right? So now, before we get into that, let's look at some current day applications of NLP, right? So we have machine translation. So Google Translate. I know it's infamously terrible at times, but it is quite a good thing. It is quite a good way to get a rough translation of a language, all of its faults considered. Web search. So all of the ways in which Google understands your queries, you basically don't need to key in specific queries. You can just say, if I remember correctly, right? You can basically key in lyrics of a song. It'll give you the song itself. If I remember correctly, if you just if you just type song that goes it gives you Darude Sandstorm, which is fun. But yeah, so it's kind of intelligent. It kind of gets what we're trying to talk about when we're doing web search, right? That is another application of NLP. Now, spam filters, right? So spam filters are one of the first applications of NLP. So we'll be looking at one of the models that was used for spam filtering later on today, right? And then you have chatbots. The thing is that if I remember correctly, Lambda was being made as a chatbot. And you also have many other examples of chatbots. So you basically have Replica for digital friends for people who don't have any and stuff like that. And then you have text summarization, which is basically taking a large piece of text and then condensing it down into the most pertinent aspects of it. So basically condensing down a news story into a short comment and stuff like that, right? So all of these are applications of NLP. Okay. Now, this is our problem for today. This is what we'll be trying to solve. This is the IMDb dataset. IMDb is a review aggregation site. So it basically so it has a database, it has a huge database of movies, and people can leave reviews of those movies, right? And leave their ratings. Now, for these movie reviews, right? You have 25,000, we have 50,000 movie reviews in the dataset that I have sent you. And 25,000 of them are for testing, and 25,000 of them are for training. Each review is labeled as being either positive or negative in sentiment. So this challenge is one of sentiment analysis. How do we basically tell what a person is thinking about a movie given the review that they give, right? So given a movie review, can we tell if it is an overall positive or an overall negative review? Do they love the movie or do they absolutely hate it from the bottom of their soul? So now let us basically get into basic pre-processing of the data, okay? So here's the roadmap for today. Here's the processing pipeline. So first, what we'll do is that we will convert all of the text to lowercase, okay? This is just to make sure that like just because a word occurs at the beginning of a sentence means that it's not treated differently from when it comes in the middle of a sentence. Okay. Then what we'll be doing is that we'll be removing all the punctuation. So special characters are often used as delimiters, but they in themselves aren't particularly informative of the text. They just add unnecessary complications. And for our simple model, we can't really deal with that. So out they go. We'll also be removing stop words. Now, what is a stop word? A stop word is a word that occurs very, very, very frequently. Okay. So stuff like is, as, and, between, all of those like very, very common words, right? Those are referred to as stop words in NLP. We try to remove them when we're dealing with like traditional NLP based modeling because they aren't particularly informative. If I basically tell you that a sentence contains like two ands, right? What can you tell me about the sentence? Nothing, right? Except maybe it's listing things out, but still not much. So out they go again. Then what we'll be doing is that we'll be lemmatizing the words. Now, what is lemmatization? Lemmatization is basically the process of reducing a word down to its base form, okay? So let us basically take the word run, for example, right? So if you conjugate the word run, you basically get runs, you get running, will run, and stuff like that, right? So what lemmatization does is that it just like condenses all of them down to their root, which is run. We do this also to make sure that like we keep the overall meaning of the sentence while reducing the total variety of tokens. Because if we had to basically take running and runs and will run, all of them separately, right? We'd basically end up eating into our memory as well. So which is why lemmatization is also another way by which we can process the text. There is another method rather than lemmatization, because lemmatization is context sensitive. It basically condenses the words differently depending on how they actually occur in the sentence. If you want something that's cheaper, right? Cheaper computationally, you may want to look into stemming the words. Stemming is just truncation. You just like cut down the word no matter what it is, no matter what it looks like. You just cut it down to the closest base. That's it. And then finally, we'll get the counts of each word. We'll get the counts of how many times a word occurs in a review, and we'll get the counts of how many times the word occurs in the entire corpus, which is basically the entire data set in our case. Okay, so now it's time to look at the Python notebook. Okay, so once everyone is done with setting up their environment, right? We can basically start loading in the data, right? So we basically have this. So we basically load in the data using the Python, using the pandas library of Python. So we loaded into the variable full data. Okay. We rename the columns to text and sent, right? And then we split the data into a training set and a testing set. Okay. This is just to make sure that we can train a model on some data. And then we check the performance of that model on that data to see whether it's actually learned something or if it's just memorized, which is a problem that can happen with more complicated models. Then we want to actually have a look at our training data, right? So we run the train data.describe function. What describe does is that it basically gives you a count of all of the things. It gives you the number of unique data points in each one, right? And then it also gives you the frequency of the most common occurrence here, okay? In this case, right, you basically have 12,517 occurrences of negative sentiment, which is about what you'd expect from a random split, right? Because there are 25,000 total entries in this data set, right? Half of them are positive, half of them are negative. Half of 25,000 is 12,500. So this is a pretty well-balanced data set. If the data set is imbalanced, you need to account for this. And there are ways such as like weighting it or data augmentation and stuff like that you can use. But that's beyond what we'll be doing for today. So here is the basic text pre-processing, right? So what we do is that we convert the text into a lowercase by using text is equal to text.lower, right? Then we basically do this. Okay, so this is something called regex. Regex is something that has been referred to as a write-only language because it's inscrutable to read. But what this regex does is that it just takes in whatever's between angular brackets, right? And it converts that and it just removes it. The reason why we want to remove everything in angular brackets is because HTML is written in angular brackets. All of these reviews were scraped off of a website. So unfortunately, they do have some HTML tags in them. Yeah, it's okay. Yeah, join in. Okay. Okay, so we basically have punctuation. So then what we do is that we've removed everything in angular brackets. So this is basically like we are removing all of the HTML and we're removing all the HTML tags, which don't really say much because they're just like bolding, they're for break lines and stuff like that. So not important. Then we'll also be removing all the punctuation. So this is a regex. This is basically, again, another like regex expression to remove all the punctuation from a string. Okay. And then finally, we'll be removing all the punctuation and we'll be replacing it by an empty space. Right. So once we basically like run all of this, right? Right. So we just need to run all of this on the training data and the testing data. And then if we basically see train data, right? Yeah. So you can see that, yeah, Congo is based on the best-selling novel. So you see that we've actually removed all the capitalization. We've also removed all of the punctuation from this data set, which is good. Next up, we need to remove the stop words. Now, what are the stop words exactly? The stop words are basically the so we basically installed the stop word. So if you look at the imports, right? We do NLTK.download stop words. This imports the stop words from the NLTK package that we can then start using inside our environment. So we basically like use these stop words. We create a set of the stop words to basically check membership. Then what we do is that we basically say we convert the text tokens into a list. We convert the text into a list of words. Word tokenize basically just like takes the list, takes the text and then converts it into like a list. Takes the text and converts it into a list. Let me just like show you so that it makes sense, right? So word tokenize. Yeah. So you see what word tokenize does, right? It basically like splits it up into hello world. So this is what word tokenize does, right? So then what we do is that we then say, okay, fine. My name is, okay. So we have this, right? So then what we do is that we basically say, I want to basically include every word inside a list, right? But I don't want the word if it is in the stop words, okay? So if I basically do this, right? So if I do a similar thing here, so remember the output of this first, right? So x4 x in word tokenize hello, my name is. If x not in oh my god. My God. Okay, yep, here. So you see, right? We've actually been able to remove is my. The two words is and my, right? From this, because they both were considered stop words. They occur too frequently, they aren't informative. Okay. So what we do is that we apply these on the tests and our training data as well. Now comes the lemmatizing. Let me just insert one more thing here. Okay. So now lemmatizing text, right? So let me just open up WordNet Lemmatizer. Let me just create an instance of that, right? Give me any sentence, any example sentence. Okay, let's first consider running, right? So what would this reduce down to? Ah, okay. Dot lemmatize. Running, right? So it reduces it down to its base, right? Going on. Okay. Any complicated words that you guys know? I mean, it is complicated, correct, but then it doesn't break down in the lemmatizer because complicated is the base. Anyway, right, we can always look at the examples from the training and the test data once we run the lemmatization on them. Okay, this will take a while. Okay. And then finally, what we do is that we basically then take a count vectorizer. So we basically just say, okay, fine, I want to log all of the words and the frequencies. This is to basically say that it needs to occur at least 10 times in the corpus for me to include it, because I don't want a ton of I don't want a ton of one occurrence words. Okay. Okay. So we basically run fit transform on the training data and fit transform on this test data to get our count vectorizer. Okay. So this basically gives you all of the counts of each one of the words and it converts it into a vector. Okay. So if I could examine this, right? Same text, right? Dot dense. Dot two dense, if I remember correctly. Okay, if we examine train vect, right, we basically see that it has 25,000 rows and 16,260 columns. Okay, so each one basically contains the number of times that particular word has occurred in that particular okay, sure. So if you had to envision it, right, it's basically having each one of the columns representing a particular word, okay? And each one of the rows represents the review. If there is a 1 in a particular point, right, that means that that particular review has that particular word occurring once. A 2 in that basically means 2 times, so on and so forth. So we store it as a sparse matrix because understandably there will be a lot of zeros over there. And we don't want to waste time or space putting all of them we don't want to waste time or space, quite honestly speaking, because I'm pretty sure that if I did this, my computer would crash. Yeah, it doesn't have enough space in the RAM. Yep. Not now anyway. So yeah, this is how the count vectorizer works, right? So we basically got into getting the counts of each word, right? Now it's basically time for our text tokenization, okay? So what is text tokenization? Okay. So the thing is that machine learning models understand numbers very, very well, but not letters or words. So how do we convert letters and words into numbers? That is the purpose of tokenization. That is what tokenization is for, right? So tokenization, in tokenization, right, we have the value counts of each word in the corpus, okay, in the entire set. Okay, now given that like every word that you add, right, into the corpus comes with a ton of memory cost, correct? Do we want to include rare words? Yes or no? So that's a trade-off that we need to make, right? We need to basically, everyone will set the line differently, correct? So the thing is that like, an obvious answer is to just simply drop all the words that occur rarely. Because it's not going to, because why do we want to take on that extra burden, right? The reason why is that we may harm the performance of the model if we drop too many rare words. For example, right? If you see the word movie inside a review, obviously you're going to see the word movie inside a list of movie reviews, right? So it doesn't tell you anything. It conveys very little information. However, if you see the word Tarantino-esque, you're not going to see it in very many reviews, but then you know what you're going to get, right? It's very informative. So how much of a trade-off are we willing to make, right? Because this guy is going to appear what in at most 20 reviews in the site. Keep in mind, these are internet comments. They don't, most of them don't have that big of a vocabulary. So we do want to include these guys because they do have value to us. They do add value to our model. So we need to come up with a compromise, and this compromise is TF-IDF, right? So to sum up, right, rare words, each word becomes a feature, which is good because the model learns from more things, but it's also very memory intensive. Common words, every word so the thing is that like the good thing about it is that each word shows up everywhere. So you learn about every single review. The trouble is you don't learn much from common words. There's not much information that's carried in those common words, right? So TF-IDF weights each one of these words, okay? So TF-IDF is broken up into two parts. TF stands for term frequency. Term frequency is, and IDF stands for inverse document frequency. Term frequency basically is how many times does it occur in a particular text string, okay? Inverse document frequency basically means how many times does it occur in the whole corpus, okay? The more it occurs in a particular text string, right? The weight of it goes up. The more it appears in the entire document, inside the entire corpus, right? The more times it appears in different reviews, it gets downweighted. Can anyone tell me the reasoning why? Like, why do we want to downweight words that occur frequently throughout the entire corpus? Yes. So effectively, like they kind of become a new type of stop word, right? Because they don't really tell you much information anymore. So that's why we want to downweight we want to basically lower their weight. If a word shows up only in the context of a couple of movies, right? And then like it occurs many, many, many times, you know that for those movies, you want to pay extra attention on that word, right? It could basically be like a movie that has like a time loop plot. And then like everyone's talking about that. And a movie about that sort of gimmick is going to live or die on that plot, right? So you want to basically look more at that word when you're trying to decide whether or not the movie is good or bad, correct? So that is basically what TF-IDF allows you to do. So you basically need to come up with like, so it lets you compromise effectively. It lets you compromise between too many features versus not enough informative features. Okay. So now we basically can go back and then, yeah, so to set up the TF-IDF vectorizer, you can just like set it up using the TF-IDF vectorizer from scikit-learn. Should be pretty easy to set up, right? And then you basically have this, so you just do dot fit transform on the train data as text, and then you transform it on the test data set, okay? Everyone clear so far? Okay. Then moving on, right? We basically have the basic. So now we'll talk about one basic model. This model's also been used for spam detection in the past. So I want to basically like talk about it in the context of NLP, okay? And that is a naive Bayes model. But to understand naive Bayes, we need to understand Bayes' theorem. Now, I don't know how many of you have heard of this very obscure game, but then, okay, so so the key idea behind Bayes' theorem is to update our probabilities given certain information, right? Now, let us basically take this example right over here. I don't know, this game is pretty obscure. So anyway, right? So we basically have certain assassins, and then the assassins have a chance of being suspicious, as do non-assassins of being suspicious. So now the key idea of Bayes' theorem is that we update our probabilities, we update our knowledge based on given information, right? So let us say that I chose a person directly from this lineup, right? From all 12, I just chose someone directly. And then I ask you, what's the probability that he is an assassin? What would you say? What is the probability? 1/3, right? Yeah, 1/3. So that's 33% chance, right? That a random crewmate is an assassin, right? Now, let us say that I told you that someone was very suspicious, was being suspicious. Now, what is the probability? 60%, right? 3/5, 60%. So keep in mind, right? We have improved our confidence of a particular outcome given certain information. That is the heart of Bayes' theorem. Knowing that a certain crewmate is suspicious lets us be more certain of him being an assassin, right? Then, okay, let's continue this, right? Now, what is the probability that someone is suspicious? Why 5/7? What is the probability that 5/12, right? Yeah, 41%. Now, what is the probability that a crewmate is suspicious given that he is an assassin? 75%, right? Again, we've improved our certainty of a particular outcome given other information, correct? Now, here's a quick summary of it. So we can only see if someone is suspicious. Keep in mind, we don't know who is the assassin, who isn't an assassin, right? So how can we calculate P assassin given suspicious, which is what we want? So the thing is that, like, let us say that we know the probability that someone is suspicious given that they are an assassin. We know the probability that someone is suspicious, and we know that the probability that someone is an assassin, right? Then we can basically say that P assassin given suspicious is equal to P assassin times P suspicious given assassin divided by P suspicious. So, yeah, so this is just Bayes' theorem. This is the probability that a hypothesis is true given some evidence E, right? Then we basically say that it is equal to the probability that the hypothesis is true. This is what we call our higher probability, right? And this is our posterior probability. So this is trying to figure out. Then we basically say that this is the probability of seeing evidence if our hypothesis is true. Let us say that we assume that this guy is an assassin. What is the probability of this event happening, right? And we have to divide the entire thing by the probability of observing the evidence in the first place. The key insight that naive Bayes has is that it realizes, hey, these two guys are constant. I can just say that PHE is proportional to PEH. So that basically means that now we can basically start thinking about what this means in terms of movie reviews, right? For example, right, what is the probability that, so let us have a movie review, right? Originally, our higher probability is just going to be 0.5, right? Of it being positive or negative. Now, let us say that the word terrible appears in the movie, right? Now we can basically say it was 50%. Now we have to update our beliefs, right? Based on the fact that we now know that the word terrible is in the movie. What happens if the word terrible and the word what if the word terrible and terrible actor also occur in that same movie, right? Then we need to update our probabilities more, right? So the thing about naive Bayes is that it assumes that all of these are independent of each other. So you just multiply them out. So you end up getting, what we know is the probability of a word occurring, right? And what we want to know is the probability of a review being positive or negative, okay? So using Bayes' theorem, we can figure out the probability of a review being positive or negative given the words that occur in the review, okay? Now you might be asking, why is it naive, right? This is the formula for naive Bayes, right? It's basically saying P of H given E is equal to P of H times P of E given H, right? Times P of E1 given H times P of E2 given H, and so on and so forth, where E1, E2, E3 are like sub-events inside event, okay? So this whole thing, right, does not take into account the position or interaction between terms. That means that to a naive Bayes model, right, the following two are the exact same. Oh, nice. Dog eats food and food eats dog. Exactly the same to a naive Bayes model. It does not care. So this is a problem, but not as big as you would think it is. So now let's actually look at how a naive Bayes models performed, right? So for the first one, so I gave you two models to look at. One is the naive Bayes model that is fit on just count vectorizer. I did not weight the terms for frequency. So you can see that this performed pretty well, honestly speaking. This is the confusion matrix. This basically gives you the true labels on the y-axis and the predicted labels on the x-axis. You want to be here or here. This is basically like it was false. This is a false positive. This basically states that this is a false negative. So we want to be here, the true negative or the true positive. So you can see that the accuracy is actually quite high. If I had to estimate, it's around 81% for this. For this one, right, we actually see a small increase in accuracy. I think that's around 82 or 83% by including the weighted vectors for these training the naive Bayes. Okay. So looking at the code over here, we basically instantiated our model as NB model. We created a new instance of multinomial by naive Bayes, right? Then we basically fit the model on the trained vectors and the trained labels, right? Then we basically got the predictions from the model, right? And then we created a confusion matrix for this naive Bayes model, right? And then we basically like created a display of this, which is like this nice plot over here. Otherwise, if I had to display the matrix, it just becomes, I have to put print here in CN, right? Yeah, so otherwise it just comes out as this thing right here, which isn't as impressive as this, right? And then we just plot it out. And we did this, and we did the exact same thing for the TF-IDF weighted one. So you actually see the TF-IDF does give you a small increase in the performance of the model, right? But then for this particular data set, it's actually still very good. The performance is still quite good, honestly speaking. So now, this is where we get into the more current sort of models. So now the attention model, the attention mechanism actually was, it's been around for a long time, but then there was this paper, if I remember correctly, it was Vaswani et al. In 2017. Attention is all you need is the paper that basically talked about how attention itself can actually, how the attention mechanism can actually help improve the performance of a model, right? What is attention? We'll get into that right now. So here's a key insight, right? Computers suck at natural language, but human brains are excellent at it. So why don't we try to mimic the human brain? This was the rationale behind stuff like sequence classification, behind stuff like image classification and stuff like that, text generation and stuff. So this basically led to the development of neural nets. So in neural nets, right, you basically have many small units called neurons. And they basically are stacked on top of each other, like human neurons. The thing about human neurons is that each one of them is pretty weak. But then when you join many of them together, you have billions upon billions and upon billions of synapses in your brain, right? So you basically have, so it is because of these like connections between these many weak sort of learners that you can construct increasingly complex functions. And that is the basis behind neural networks. So neural networks, if you look at the literature, right, they basically have a huge amount of success when it comes to a lot of different types of tasks. And we'll be seeing this soon. So as for attention, right, the key insight behind attention was realizing, hey, position actually matters, right? It's a key factor in language. Bird eats insect means something completely different from insect eats bird, which means completely different from insect bird eats, in which case you're Yoda. Right? So attention allows for us to incorporate position, some notion of positionality into our model, right? So attention models or transformers, not 100%, but then, yeah, for the purpose of this, let's call it a transformer, right? They are made up of two parts, right? So your input goes into an encoder. The encoder basically just crunches up the input in and tries to extract the most useful information out. It passes along that information to a decoder that tries to get an output out from it, right? So now, how do we know what to pay attention to, right? How do we know what needs our attention, right? So attention models basically convert every word into a token. So we know what a token is, right? It's just like just compartmentalizing the word into like smaller parts, right? So you just like take hello world. In hello world, you just take hello world, right? And then you just like compartmentalize them into their own tokens. And then you just pass them into the encoder. The encoder basically returns you something called the query, right? Now we have key and value vectors. So each key is mapped onto a value, right? It's like a dictionary. There's a key value pair, right? What we need to do is that we need to figure out what key the query is most similar to, right? So you basically have the decoder that provides you the keys, right? And you basically need to match the query to the keys, okay? So how do we know what is relevant for each query, right? So we need to come up with some form of score, right? And here we actually get inspired by search engines. So here's how the attention mechanism works on a very broad level. We can go over the math and the specifics later, but you basically have, from your encoder, you get your query, right? The query gets mapped onto the keys. Where do we get our keys from? We get our keys from the decoder, right? Then we basically get from our keys, we can look up the values, right? And then we multiply the query and the values together to get our final output, okay? Which is the score, right? The score basically tells you how much each part of the query matters when it comes to the output. Okay. So I am aware that was like a little bit, that was quite fast. And like this usually would take a workshop on its own. But then right now, we don't actually need to deal with like the details of the inner workings. Because right now, what we're going to do is that we're going to steal a model off of we're going to steal a trained model. We're going to steal someone else's hard work. We're just going to train it on our thing for a little while, and then we'll be able to get the answer as well. Okay, so here's the tokenizer, right? So we basically so we just like use the Hugging Face Transformers library to get an auto tokenizer from a pre-trained. So I'm using I'm using a pretty small version of BERT called Distill BERT. It's 40% of BERT's footprint, which is still massive. And then you have the model for sequence classification. So I'm just loading it in and I'm just telling it, I want the one for two label task. Okay. Then I'm going to load in the IMDb data set, right? And I'm also going to define a pre-processing function. The pre-processing function basically just feeds in whatever values I get from my IMDb dataset, and it's just going to toss it into the tokenizer. Okay. Then I'm setting up these training arguments, right? So basically, like all of these are things that we can look over later. And then we've also set up a trainer, right? So then after that, we just like let it train. And yeah, it's just done training. Okay. So we can basically look at our model, right? So model of okay, so this is after the model has been trained. So this took a while to train, and that's because I just did it on my local CPU. If you do it on Colab, if you do it on GPU, this takes 10 minutes. Okay. So if I just do trainer.test, right? All right, let me just like quickly check because I have forgotten the trainer eval. Yep, sorry, I just forgot the API. Oh, dot evaluate. Evaluate. It's not. Let's evaluate. Okay, we can look at this guy later on. Okay, but then now it's for the fun part of the presentation, which is the current models that we have out right now. So far, right, transformers are like the state of art for NLP. So Vaswani et al. Actually like brought about transformers in 2017. 2018, they improved encoding techniques using BERT. 2019, you have XLNet Ernie and as well as GPT-2, which is like the precursor to GPT-3, which was released in 2020. And in 2022, you actually have Lambda, which was released, which was the which was the one that actually like caused quite a stir lately. So here, right, we basically have GPT-2. We have an instance of GPT-3. So OpenAI, you can actually access this. You can like go log in using Google. You have $20-ish of free credits that you can use for OpenAI. So here, let's look at some what would you guys like to try? Okay, so this is like another, this is a passage from the Wikipedia page for Jupyter, right? So we're asking GPT-3 to now summarize this for a second grade reading level, okay? Yep, okay. So any Wikipedia pages that you guys want me to look at? Okay, which one? Attention? This is probably going to explain it better than I did. Yep. So this is the summary that GPT-3 was able to come up with. Okay. Anything that is famously very hard to read. Anything that you want. Hey, Shakespeare is fun. Okay, fine. Mark Antony's speech. Let's do this. Yep, Brutus's stuff. Yeah, let's see how this goes. Let's have a look at how GPT-3 handles this guy. Okay. Pretty spot on, right? So what's the point of making this making this thing like is it just a conversation for that or is it like oh no, there's a ton of usage for GPT-3. Like this will power a lot of different sort of like products like chatbots. This is very good at translation. Okay, fine. Anyone know a second language? Okay, what language? Tamil, right? Okay, so okay, give a sentence and then like let's see, and then just verify if it's a proper translation. So what sentence in English do we want to translate into Tamil? Huh? Where is my computer? Okay. Nice. This basically works where this shines when it's like even more complicated, when it's even more complex. Which where? Where?
The meaning of the last word is basically how many. The question was where, but the answer became how many. Like the meaning itself is wrong.
I see. Okay, it's still a work in progress. Especially, I think it's not very tuned for like yeah, how do we put this? Like non-Europeans, let's say. Malay. Okay. Hindi. Okay. Oh. Okay. Yeah. It's still not 100%. Is that accurate Italian? Okay, German was also one, right? Wo ist mein Computer? Oh, makes sense. Okay. Okay, yeah. So basically, right. Okay, I am, and then like you have all of these parameters over here, which basically talks about like how which you can use to like tune various aspects of the model itself that you're trying to do. And they also have an API that you can actually call from other things here. So like if you want to like incorporate some sort of like autocomplete and stuff like that, you may want to like try using these APIs. Although they may be kind of expensive. GPT-2 is slightly weaker, but it is free. It's open source. GPT-3, you need to pay slightly, but it's still very good. And I think that GPT-3 is actually currently, I won't say it's outdated, but now there's Lambda, which is even more cutting edge. I think it was just released, and I think it's like limited access right now. Okay, yeah. So that basically brings us to the end of this presentation. So, anything that you get, any questions about like the whole presentation as a whole? To connect different parts of the paragraph, you need to understand what's the relation between the. So there's a but, what if there's an and, that might change the meaning. Right, and that is why naive Bayes and stuff struggles. Transformers you don't usually remove stop words in transformers, because transformers can downweight those stop words for you. They just reduce the weights, but then they still keep some of the meaning in there.